to the video presentation of the 13-2 Isosceles Triangles lesson, and our objective is to develop and prove theorems about isosceles triangles. You know, those triangles that have at least two congruent sides. So we'll be looking at some specific properties of isosceles triangles and applying those also to equilateral triangles, because equilateral triangles are also isosceles. Is that confusing? Well, hopefully this lesson will clear that up for you a little bit here. Okay, so you can see over here on the right-hand side, we have a couple of springboard book pages and then our good old challenge problems. All right, so let's take a look at the objective slide for our one and only objective for this lesson, developing and proving theorems about isosceles triangles. All right, right down below the text, you can see a picture that has this grayed out triangle ABC. That's the isosceles triangle. The picture here is taken from Euclid's Elements, which, of course, in classical times, if you're going to learn mathematics, this is the place where you go, right? Is the only set of books that existed that contained all of the math knowledge up to that point. So the etching that's over here on the left-hand side, and it has some strange-looking guy. Looks like it may be an artist or something that's holding a palette. He's falling off the top of this thing. There's somebody that's hanging in the background. Down below, you see all these donkeys. And right down below here, it says in Latin, Pons Asinorum, which translates roughly as the bridge of asses. And that's referring, of course, to the donkeys that are down below. So all of this refers to the fact that if you were going to learn math, again, it would be in Euclid's Elements. And you came to the point where you had to prove something about isosceles triangles. As a matter of fact, it's what this lesson's about. It's the base angles theorem. Some people just couldn't understand the proof at all. And it came to be known, this problem itself came to be the distinguishing factor, whether or not you could, like you were bright enough to continue your academic career, or whether or not you had to perhaps do something else. Pons Asinorum. All right, so let's take a look at the definition, formal definition of isosceles triangle. Make sure to write something down here. A triangle is isosceles triangle if and only if it has at least two congruent sides. Okay, so this definition, the formal definition here about it having at least two congruent sides, the misconception is that it has to have exactly two congruent sides. However, for this particular definition, let me come over here to Notepad so that I can write something down here. Since it has at least two congruent sides, this means that every equilateral triangle is also isosceles. Do you struggle with spelling the word isosceles? I do too. There's so many S's and C's and whatever. Those things don't go together. Every equilateral triangle is also isosceles. So we can see that we have an equilateral triangle over here on the right-hand side. The green marks there are actually the compass marks that you would use and actually to construct this thing. That'll be part of this lesson coming up. And this fact here that I just wrote down is going to be central to a theorem later on in the lesson. Okay, but kind of like with rectangles and squares, but not every isosceles triangle is equilateral. And the triangle over here on the right-hand side demonstrates that fact. Okay, so the triangle that's over here on the right-hand side, please draw something to go along with your notes and this definition of isosceles triangle, labeling the different parts. So the vertex angle is the angle that we're referring to that's made from the two congruent sides. These two congruent sides are often referred to as legs. So here's a leg, and here's a leg, and hopefully, like isosceles triangles, your legs are congruent too. If we come over here to this equilateral triangle, which one is the vertex angle? Well, the answer to that is that any of these can be the vertex angle. So for example, this angle up here could be the vertex angle, where these two are your two legs. Or it could be Dial that back a little bit. Perhaps this one over here on the left-hand side is your vertex angle, which means that these two here are your two legs. Okay. Directly across from your vertex angle is the segment that's called the base. Now, the base in mathematics doesn't often refer to the bottom of your triangle. So, for example, this triangle could be flipped upside down, and still directly across from the vertex angle is still the base. Okay? The two angles that touch the base are called the base angles. So we got this angle over here, and we got this angle over here, the base angles. Matter of fact, our main theorem for this lesson concerns these two base angles. Okay, so now what I would like for you to try to do is this first exercise. If the lengths of two sides of an isosceles triangle are 3 and 7, what is the perimeter of the triangle? All right, so our problem here is that since we have two of the sides, we're missing the third side. Now, this particular isosceles triangle cannot obviously be equilateral because we have two different side measurements. The question is that which one of these is the base? Is it the 3 or is it the 7? Okay, so again, let's go back. And let's break this up. We basically have two different cases. So I'm going to draw one out here. Let's say, for example, in this case number 1, that the base is the smaller piece. It's this 3, which leaves these two congruent sides, the two legs, as being 7 and 7. All right, so everything seems to be fine here. So I'm going to say that the perimeter is equal to, we've got 3 plus 7 plus 7. There's 10 and 7 more. Perimeter is equal to 17 units. Whatever these units are, it doesn't tell us. Okay, the second case is like, well, what if the 7 is the base? Let me draw a case for that one. All right, so let's say that this base down here is 7, and then I go to try to draw the other two sides, the other two legs, which are 3 and 3. And I'm going to notice that they're just not long enough to stretch to the other side, right? They don't span this length of 7. The most that they could ever span is 3 plus 3, which is 6, right? So like it would reach right here, it would reach right there. There would always be this 1-inch gap that's right here in the middle. So this doesn't even make a triangle. So case 2, we don't even have a triangle. Which means our winner is a perimeter of 17, where the 3 is the base and the two 7s are our legs. All right, exercise 2, what I would like for you to do, if you haven't gotten them out already, is to take out your straight edge and your compass. And with your straight edge, you're just going to draw yourself an acute angle, like so. There we go. And then I want you to see if you can just take your compass and your straight edge and turn this acute angle into an isosceles triangle. And there's multiple ways to do it. I would like to see what it is that you come up with. So I'm going to stop this video here, give you a moment to gather your supplies, and give this investigation a try.